Hi, this is Team Second Degree. I'm Nick Davis.
And I'm Nathan Kanekuni.
For our project, we created a store database and a Java program which retrieves information from that database. And we have a bunch of different queries that we ran on it. We have the inventory of a store, we have the stock of certain SKUs, and then we have, for stores, we have where the stores are, who the store managers are, what their utility cost is. For our employees, how much they make, how many hours they work. And then our main focus on this whole entire project was sales analysis of, so we can check how much our store makes or how much it doesn't make, if something's making profit or not making profit, and what years we make more profit than others, and actually the total net profit of our whole entire store. For the first iteration through the project, we just used static SQL, and we didn't add any optimization features such as indexes to it. But our second iteration, we actually changed the static SQL into dynamic SQL, so we can have more queries with less actual code, and we did some error checking because with dynamic SQL you have to make sure that that when they enter something they enter a correct value, because if they don't, either it'll return nothing, or if they put in something malicious it could drop your tables or delete your data. And we also added optimization so our queries would run faster.
So this is going to be the demonstration portion of our project video. Right now I have currently our first iteration of our project running. As you can see, we have 10 different queries to express the inventory of our stores. We implemented this using static SQL, so we had to write 10 different queries to express the 10 different parameters in each of the individual queries. To use the program, we simply type the number over here that corresponds to the query that you want to run. So if I want to find the inventory of store number 8, I'll type 8. And it will display to me the inventory of store number 8. I can do 3 to see the inventory of store number 3. To see one of our more difficult queries, here we have query number 34. Which store had the top net profit in December 1999? So I type 34, and it tells me it was store number 5. Now, we didn't list all the possible combinations of queries here because it just would have been unfeasible to code that many queries. We have 12 months, and our sales history goes back to 1970. So we have 43 years times 12 months. That would be about 500 different queries we would have had to write to express this statement. To correct for this, in our second iteration, we decided to use dynamic SQL so that the user could specify these parameters, which would greatly reduce the amount of code we needed to write, and it would also add more functionality. So, as you can see here in our second iteration, we no longer have 10 different queries to show the inventory of our stores. Instead, we only have one query, which is the inventory of stores. So I can type 1, and the program will ask me to input a store number. I can put 3, and it will tell me the inventory of store number 3. I can put 7, and it will tell me the inventory of store number 7. To see some more difficult queries that we've written, which are the ones that specified months and years, we can look to query number 21. Which store had the top net profit in a specified month and year? So I type 21, I type a month number, so March 1999, and it will tell me which store had the top net profit in the specified month and year, March 1999. I can also do this for another month and year combination, and it will give me the answer for that particular month and year. We also have a query that tells us what is the total net profit for our entire chain. Now this query is actually a static. It uses a static SQL in our second iteration. We didn't use only dynamic SQL queries. This query basically tells us that our store chain, since the day it was founded, made $61 million. Yay. We also have another query over here, query number 24, which tells us what percentage of the total profit does each item make in a specified month and year. So by typing 24, I will input March 1999, and I can see for every store and a given SKU what percentage of the total profit that item makes for that store. Okay. Also, we implemented a timer class to check how long our queries were taking to run. This is important because later on we did optimization and we needed to see if we were making improvements. Our query number 23 has this timer, and it tells us that it took 31 milliseconds for this query to run. Okay. So dynamic SQL is pretty nice. It lets the user do inputs, but we also have some problems with dynamic SQL. One of the problems was error checking. So if the user inputted something that DB2 was unable to understand, we would not get a result set back, and our program could potentially crash if we didn't handle that exception. To correct for this, we decided to do extensive error checking. If a user inputted a SKU, store number, employee name, what we would do is we would run another query which would check to see if that input was already in our database under like the list of SKUs, employees, etc. We also did other error checking for months and years and other values, but we might not necessarily use the database for those error checkings. So now I'm going to give you an example of our error checking mechanism. So query number 2 asks us, what is the stock of this SKU across all our stores? So I input 2, and now it asks me for a SKU. So what if I didn't know a valid SKU number? I'm going to type in this. It tells me the input is invalid. Input a proper SKU. So let's just pretend now that I know a real SKU, like 103. And it tells me the stock of Hello Kitty Online Adventures at all of our stores. Now, let's suppose that I didn't actually know a valid SKU number. Like, I'm struggling here. I don't know what to do. We have this exit clause where you can just type exit, and you can return to choose a query, and press 0 to see a list of queries again.
After doing dynamic SQL and error checking in part 2, we decided the next best thing we can do is optimize our queries so they can run as fast as possible. We used our sales table for this since our sales table has over 26,000 records in it. Our sales table looks like this, with a store number, SKU, year, month, and num sold. Our primary keys in this were store num, SKU, year, and month. And so we ran through the query, select SKU from sales where num sold is greater than 175. So this is a range query. And when we ran this range query, the optimizing plan just decided to run through the table and just pick out the ones that were above 175 and return them to us. And so then we created an index on num sold to see if that would change the optimizing plan. So it changed it to use the index, and it ran through this, and it used the index to find all the things. The thing is, though, this actually ran slower than the no index one did. So we ran run stats on this to see if it would change it, and it changed it back to the first one since it's faster, since it's a range query. The reason why this is because with an index on num sold, since it's unclustered, it'd have to access different pages based on the index. So it'd have to run through the index and then find the tuple to return, instead of just running straight through and returning the tuples right away. And so then we decided to use a point query, and the point query that we used was select SKU from sales where num sold equals 150. So it's basically the same exact query, it's just with an equal sign instead of a greater than. And so the first path that DB2 chose to run through this was it just went straight to the table, returning all the ones that were equal to 150. And then when we added an index on it, DB2 changed its optimization plan, so it used the index. And so it used the index to go through everything and fetched them one by one that way. And so then we decided to do run stats again to see if that would change it a different way, change it back depending on what DB2 wanted to do. And it didn't change the query at all. And so we actually kept times of how long it took to do the point queries. So the first and second iteration with no index, it was about the same with 213.9 and 232.7 milliseconds, which isn't too big of a difference. And then with the second iteration, when we put the index on, it actually only ran in 70.6 seconds, which is quite a bit better than the first one. So using an index and a point query for ours is a lot better.